470 class this semester. Some of them are here. I didn't require them to come here, but because it is the first time. It's actually the first time I've taught a graduate level class here in 15 years, which is kind of remarkable. Actually, I guess optics, when it was 30 whatever and 60 whatever, may have counted. But in any case, I really feel like this was an intellectual challenge for me this semester, and it's in large measure due to those very fine students who have challenged me to learn and relearn a lot of this stuff in a way that actually makes it coherent and explainable. So that's my first acknowledgement. I'm going to tell you a little bit about my favorite subject, which is alkali-metal vapors. I've been working on them pretty much since I was in graduate school in the area of optical pumping and spin exchange and various applications of polarized vapors and polarized noble gases. And I'll take you through all of these little diagrams here as we go. So just to orient you, to remind you, the old periodic table, and the alkali metals are sitting way over here on the left. And these are the guys that come after all the closed shells represented by the noble gases. And so the property that they share is that they have one valence electron, one unpaired valence electron in an external shell. Hydrogen is kind of special for reasons that I'll talk about in a moment. But for the most part, what you're looking at is electronic states in these atoms that are fairly straightforward, hydrogen-like, if you account for the fact that the nucleus has more positive charge and there's shielding and so on. Okay, so let's take a look at this column 1 group. So I tend to focus on rubidium because I work with it most often. And I'll say something about these heavier alkalis and how they're the real harmonic oscillators of the periodic table. So looking at the basic structure that they all have in common is that there's a ground state that has some principal quantum number, and the principal quantum numbers are noted here as you go down the table. That's an S, all singlet states with a total angular momentum 1/2. That's just the spin of the electron. And it has a first excited state that's a p state. And in all of these alkali metals, the n of the ground state and the n of the first excited state are the same. It's 1 and 2 for hydrogen. And they all have this fine structure splitting in this first excited level. So this is just angular momentum addition. This is an L equals 1. That's a p state. So you get 3/2 and 1/2. It turns out, because of the direction of the electron magnetic moment relative to its spin, it's the 3/2 state that has higher energy in all of these things. And then I'll just remind you, spectroscopic notation, principal quantum number. Here's the orbital angular momentum, SPDF. Here's the total angular momentum at lower right. And then 2s plus 1 indicates a singlet, triplet, or a doublet. These are all doublet spin states. You just have one electron that's determining the whole thing. So in atomic physics, we look at and pore over and study oftentimes these things called Grotrian diagrams. They're basically energy level diagrams. And I'm showing you two, one for hydrogen and one for rubidium. And in these diagrams, what one typically shows is, these are partial diagrams, mind you. One shows the energy levels. And here we can see hydrogen, and the ground state is at minus 13.6 eV. Hydrogen has a very, very tiny fine structure splitting compared to the heavier alkalis. And the other thing that often gets showed on Grotrian diagrams is oscillator strength. So what you see here, you see the transitions and the energies measured here on the right. And you see the wavelengths along the line. And you also see these relative oscillator strength. I'll talk about what that is in a moment. Here, compare that to, this is a simpler, even more simple Grotrian diagram for rubidium. Notice, first of all, that of course, the ground state energy is much, much higher at minus 4 electron volts. The rubidium electron is farther away from the nucleus to begin with. And, of course, it's at least somewhat shielded by the inner core electrons. And so there's a smaller ionization energy for this. It also has, as we said, it has a fine structure that ends up being a separation here of almost 15 nanometers, okay, compared to hydrogen, which is much, much smaller. So I want to talk about this oscillator strength. Huh. I wonder why the 3 is red. So oscillator strength, here's the formula for it. And the way you to think about it is it's just putting all of the wave function properties of transitions, of these electric dipole transitions. So I should say that too, that these transitions, of course, are all first order allowed electric dipole transitions. D1 and D2 are the names of these transitions. And the oscillator strength is just a way of separating out and quantifying all the details that have to do with the specific wave functions of the atom. Okay? And you can see that the matrix elements connecting the initial and final state, that's a big part of this, the sum of these. And then, of course, the thing that goes in the middle is the dipole position operator, which is computing essentially the electric dipole operator value for these transitions. And then there's some constants in here too. And there's a sum rule that says that all of these things, these oscillator strengths from a given level to all other levels in the atom have to add up to 1. And the thing to notice here about rubidium is that it really is, if you take into account fine structure, so there's factors of degeneracy here that have to be accounted for. But this S to P transition, all of the oscillator strength in this level is with this one, actually, pair of transitions if you include the fine structure. And if you look out the rest of the Grotrian diagram of rubidium, there's nothing that has much of an oscillator strength more than about 1%. Okay? And you can see that it adds up, 6732 adds up to 1. And this ratio 2 to 1 simply reflects the ratio of the degeneracy of the 3/2 level to the 1/2 level. Okay? So compared to the degeneracy of the ground state. And so really, you could say that this thing really, compared to hydrogen, which has oscillator strength all over the place in these transitions, and then the one that would be the canonical one, the S to P, it only has 0.42 combined for both of these transitions. So what are we saying? So the rubidium atom looks a lot like a harmonic oscillator. It looks a lot like an electron on a spring, for real. And if you ask yourself why that is, normally when we reduce our analysis down to something simple, we want to go right to hydrogen and say, well, hydrogen's the simplest, let's look at hydrogen. In this case, rubidium is actually the closest thing we have to a real atomic harmonic oscillator. Now, I stole this diagram without shame from one of Jordan's 2210 lectures. Okay? And I can tell you why that the rubidium atom looks so much like a harmonic oscillator. And it's because it's shielded by the inner core electrons. Okay? And so if you've ever done this problem in 2210, where you put a hole in the earth and you drop a mass from the top and you let it drop, and what you discover is because the external mass, the mass that's at a greater radius from where you are, doesn't contribute any gravitational field, the potential here ends up looking just like a harmonic potential. And the object here will oscillate harmonically from one end of the earth to the other. Well, the rubidium atom does the same thing. It actually goes through the inner core of electrons, experiences the same type of interaction, okay, not affected by the external electrons to its radius, depending on where it is. Now, I'm speaking very classically, and I have an adage that everything's classical until proven otherwise. But I'm doing that so that you can visualize, at least in part, what the argument is. So here it is. This is our rubidium atom with its very spherically symmetric inner core of electrons, 36 of them, versus the nucleus, which of course has 37 protons in it. And here's our electron out here, and it does the same thing. It's spending a lot of its time moving through this cloud in this way, and it tends to move more harmonically for the exact same reason. In fact, it's true that it doesn't matter whether you go right through the center or whether you go on a chord here, on an angle through this sphere. This gives you harmonic motion as well. So the fact that these atoms have such, this fluffy electron on the outside and then this inner core actually makes them look a lot like an electron on a spring. And one thing that does, it tells you that these things were studied early and often, because this oscillator strength tells you a lot about whether or not that atom's going to absorb light, resonant light, how well it will, how strongly it will absorb, how strongly it will fluoresce. Okay? All right, so let's see. So I want to talk a little bit about optical pumping, which is a technique that takes advantage of the selection rules of dipole transitions, +1. And although the talk is about hyperfine physics, I want you to assume zero nuclear spin in the alkali metal for the moment, just because the initial explanation is a little bit easier. So let's go back to a situation in which we just now talk about the ground state in rubidium, this 5s1/2, and this first excited state. Nice, strong dipole transition connecting these two. And we apply a magnetic field. How big? Well, you know, it can be 30 Gauss if you want, a few Gauss if you want. It can be bigger. Generally, these are sort of typical laboratory fields for us, about 10 or 20 Gauss. And what's going to happen, of course, what should happen if we didn't have a nuclear spin in this atom, is that we would Zeeman split both of these levels, okay? And because this lower fine structure level has a total angular momentum of 1/2, this is mixing the orbital and spin angular momentum of the electron in such a way that, and you have to remember that the LS coupling in atoms is very tight and so strong. And so I'm not going to overcome that coupling with a magnetic field until I get to a very, very big magnetic field. So it's another fancy way of saying the good quantum number is going to stay the J and the M sub J, the total angular momentum. And so when I apply my small magnetic field, this is going to split into two magnetic sublevels, just like the ground state. Ground state's easy to visualize. It's just the spin of the electron, up or down. This one, of course, involves sums of products of the orbital and spin angular momentum. But nonetheless, there's just two. And if you let me write, or if you let me look at the upper level and its two, and the lower level and its two, that I'll do on the next slide. And I won't show a gap between these two levels. I'm going to put them out side by side. And I'll just remind you, this is 1.5 volts, okay? Rubidium exists in thermal equilibrium in the ground state. That's where it likes to be, all right? Because it's 1.5 volts to the first excited state, and room temperature is only a 40th of MeV. And not only that, but the spontaneous decay rate here, the decay time of these, you know, in hydrogen, the Lyman alpha is like 1.6 nanoseconds. This one is like 30 nanoseconds. It's fast, okay? It's a lot faster than any of the processes I'm going to talk about involving absorbing light. And it means that we're going to pump these atoms. I'm going to excite atoms from this state to this state. But the only reason I'm going to do it, you could say, is so that they come back. All right? What I'm interested in is the state of the rubidium in its ground state after I'm done doing all this, okay? So, right. So, see, this is, I've obviously given this talk many, many times, so I just explained this. This is 10 to 100 microvolts for this splitting and 1.5 volts here. Okay, so I put it in there. I was too smart for my own good. Okay, so as promised, here we go. Here's the ground state now with the two Zeeman levels now shown equally, even though we know there's a tiny little splitting there. Same in the excited state. And you know the selection rules are with us. Okay, so delta J here is 0, half to half, perfectly allowed. Delta L is 1. We're going from S to P, perfectly allowed. Then we're going to add an extra one. If I use, to excite this transition, if I use circularly polarized light, then I have an extra selection rule. The selection rule is that the M sub J, the Z component of angular momentum, has to change by plus or minus H bar. Okay? And so what that eliminates is transitions that go straight up and down here. Okay? So if I choose one helicity, I can drive this transition. If I choose the other one, I can drive this one. All right? So for the sake of argument and demonstration, let's say we choose what's called the sigma plus, or the, it's called sigma plus, and it's also called left circularly polarized light, and the notations are all mixed up. But the point is, it has angular momentum that follows the right-hand rule along its direction of propagation. And that means that these atoms will see this light and can be excited to this state. Now, normally what I'd say is what can happen here to these atoms is that they can decay back to either of these two ground states, and that's what I want them to do as quickly as possible. And in fact, you can see that if I just let them decay, they could decay to this state and they could decay back to this state. If they come back here, no gain, no loss. If they come back here, then I've moved atoms from the spin down electron state to the spin up electron state. I've pumped them. Now, the fact of the matter is, if you look at the way we de-excite these, we don't like to let them de-excite radiatively, because then they're throwing around all kinds of random polarization of light that we don't like, and it can undo what I'm trying to do. So we have them de-excite collisionally, okay? But before that even happens, the excited state atoms mix together and the populations equilibrate, just collisionally. And this is important because it turns out that the Clebsch-Gordan coefficient for a decay from here to here is twice that of the decay from here to here. So you're twice as likely to end up in the state you started from unless you have this nice mixing. This actually makes your photons more efficient at pumping. And so then, as I said, what happens, we do this non-radiative quenching with nitrogen. It's got a lot of rotational vibrational states. It's willing to take up all the energy without the atoms emitting a photon. And so you see, to the extent that I can suppress relaxation of these spins back to here, and that's, you know, that's a lot of PhD theses. There's a lot of work there in understanding these relaxation mechanisms. Okay? To the extent that I can control them, I can depopulate this level. These atoms can't see this light because there's no sublevel over here for them to go to. Okay? So now I have a sample in a vapor, and I should show you, I should give you some handle on what this looks like. So this is, let's see, which the one can I afford to have break? This one. This is a pretty good example of a glass cell that has, you'll see some shiny metal, silvery metal, that's the rubidium. And inside it has some xenon-129, it has some helium-3, it has some helium-4, and I'll come to what that is in a moment. But what you're to imagine, just from a practical standpoint, experimentally, is that we deal with enclosures into which I can shine laser light because they're made of glass, and that I can heat so that I have a vapor of a controllable density of the alkali metal. And I can perform this process, okay, continuously. All right? So it sits in an oven. I shine a laser on it. That's basically what's going on. Okay? Oh, I already did this. I'll do this again. And yeah, okay. So that process is called optical pumping. We are using the excited state just as a way station, just as a place to park the atoms and to let them come back down. If we depopulate one with the circularly polarized light, we end up with a population that has all the spin in one state. So just a little bit of history. These are some of the optical pumping pioneers. This is Alfred Kastler's atomic physics group at the École Normale in Paris about 1960. And he wins the Nobel Prize in 1966 for optical pumping, for the discovery and development of optical methods for studying Hertzian resonances in atoms. I love this, Hertzian resonances. It tells you dipole. That's what he's famous for. He's famous for looking at dipole resonances in atoms, and also for optical double resonance techniques. In other words, one of the first people to really use optical methods to explore some of the magnetic properties of these atoms. Okay, and so this group, this is a pretty august group, by the way. There's Claude Cohen-Tanuji right there. This is Jean Brossel, and he and Kastler, the laboratory now at ENS is named for them. This is Serge Haroche. Both another Nobel laureate in this group. This is a pretty powerful group, and there are a lot of people that did some amazing things in atomic physics after working under Kastler. What can you do with just optically pumped atoms? This is my colleague Mike Romalis, who's been here to give a colloquium, sitting in front of his sub-femtotesla multi-channel atomic magnetometer. This is based on a vapor of pumped alkali metal atoms, rubidium atoms, and potassium atoms. Potassium, for various reasons, for whatever reason, has a kind of anomalous small fine structure splitting. It works a little bit better. But this SURF, this acronym SURF, stands for spin exchange relaxation free. And so you find that alkali metal atoms, when they collide with each other, they can exchange electron spin. And this is a source of decoherence in a magnetometer where you're actually using the EPR frequency to try and sense a magnetic field. All right? And Mike was one of the first ones to put into practice this idea in a real device and actually achieve very, very long coherence times and magnetic field sensitivity down below 1 femtotesla per root hertz, which I can't say too much about except that it does rival the sort of sensitivity one gets from squids. It's a 3D apparatus. It means it can sense the fields in all 3 dimensions. And applications include, and Mike and others are working on this, magnetoencephalography, so studying brain magnetism and explosives detection. Okay? So that's just optical pumping.
What do you mean by explosive detection? I mean, it's pretty easy to detect explosives.
When they blow up? Yeah, I think like prior to them blowing up, maybe. You know. And I'd have to ask Mike more about that. I know I looked on his website before I prepared the talk, and that was the latest thing. I knew about the brainwave stuff, but I didn't know about the explosives detection. Okay. So at this point, I think it's probably a good idea just to give you a very quick refresher in NMR. What we do with magnetic resonance detection. This is very, very simple, but I think it'll be very helpful for the rest of the talk. Here's the poles of a magnet. Basically, you get some stuff that's got spin. In conventional NMR, that would be proton spins just because they have big moments and they're dense. And you throw them in the magnet and you generate some thermal polarization here, some net magnetization. So I'll remind you that each of these spins, the proton has spin 1/2, the nuclear spin we usually call I. The moment is going to look like a constant we call the gyromagnetic ratio times h bar times I. All of my angular momenta are dimensionless, just so you know. Then you're applying a magnetic field here. The Hamiltonian is the Hamiltonian is minus mu dot B. The negative sign somehow got squelched there. It's supposed to be minus negative mu dot B, and it leads to this two energy level structure separated essentially by the magnetic moment times the magnetic field. And we describe that by denoting this energy as h bar times the Larmor frequency. So the Larmor frequency is just given by the gyromagnetic ratio times B. So that frequency is linearly proportional to the applied magnetic field. And what we typically do, well, I should say this, here's the separation, or here's the two energy levels. And in typical NMR, what you see is that the excess in the lower energy state generated thermally is very, very small, actually a lot smaller than what I'm showing here. This is just for illustration. It's typically a part in 10 to the 5 or a part in a million, even in fairly large laboratory magnetic fields. The polarization that I'm talking about, assuming that we have spin 1/2, it's a simple case like protons. It's just the number of ups minus the number of downs divided by the total number of ups and downs. And if you go and calculate using statistical mechanics, the ratio, then you find that it's proportional to the hyperbolic tangent, okay, of basically it's the energy of the transition, delta E, divided by KT. So this number is always small, right? Because I said this is typically something like, microelectron volts or something like that, maybe 10 microelectron volts. And this, of course, is substantially bigger at room temperature. And actually, for nuclear spins, it's even smaller than that. So, as I said, part in 10 to the 5, part in 10 to the 6. All right? So usually, it's because this is small, you can make the approximation that the polarization is approximately just equal to this argument, which we often do. So for energy much, much greater than KT, you can just write it like this. Okay? And it's small, and what we do in NMR then is we take this polarization and represent it by a single vector, the excess spin density, the net magnetization. And in the presence of a magnetic field, we can apply a pulse of resonant RF, and that resonant RF at the Larmor frequency will nutate the magnetization away from the applied magnetic field. Now that it finds itself at some angle with the field, it's going to want to precess. It does precess, and that precession is picked up as a changing flux in a set of coils if you're detecting inductively. And you generate something called the free induction decay. So if we look at this thing, it's going to go around and around and around, and we're going to see an electrical signal that goes up and down, up and down, up and down. And of course, we also see its 90 degrees out of phase component because of this circle, if you look. And it decays away for various reasons. There's various ways in which these spins will decohere. Magnetic field gradients, microscopic interactions, gradients done on purpose if you're doing imaging, okay? But for whatever the reason is, typically an NMR signal, this free induction decay kind of looks like this. I want to talk a little bit about the Overhauser effect because I'm going to talk about spin exchange, the thing that we most often do with our optically pumped sample, which is to pump the angular momentum into yet another system. And the Overhauser effect is really kind of neat. And I was playing around with this graphic for so long that I felt like I had to show it to you. So here is, so what you have in the Overhauser effect is, and the reason I showed you NMR first, it's really true of any system where you have two pairs of two levels, okay? So in this case, and the energy separation between the two pairs has to be very different, okay? So in this case, I'm just showing two kinds of spins. There's a spin that's electron-like, that's the S. It has a big magnetic moment, so its separation is big. and there's a spin that is I, a nuclear spin with a nuclear moment that typically is a couple thousand times smaller than the electron moment. And in the regime now where the coupling between them is weak, all right, we represent the states in the so-called product basis. Just means that you say, well, there's 4 possibilities, up, 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 down, up, and down, down, okay? And they're split. This is a big energy splitting because it corresponds to the electron changing states. And here's a small energy splitting corresponding to the nucleus changing states in each case. Now what's going to happen here is you're going to compute what the thermal excess spin density or magnetization is going to be. And I'm, of course, overstating the case for display. I'm showing you that for the electrons, there's twice the number in the ground state as in the excited state. Now, in most realistic situations, it's much closer to half and half, but this lets you see that the electrons are doing all the talking. They're the ones that are saying, okay, we got to live in the ground state compared to the excited state. I'm not even showing a difference in states for the nuclei because it's so much smaller. And here it is. The polarization for the S, for the electrons, is proportional to the Bohr magneton, the big old Bohr magneton. And the polarization for the nuclei, of course, is proportional to the nuclear magneton, some 3 orders of magnitude smaller. Okay? So mu n much, much less than mu b. So what happens? Well, I can do exactly what I did in the last slide. I can apply radio frequency or some kind of oscillating frequency at the Lamarck frequency of the electrons. And if I do it a lot, very similar to any optical transition, I can saturate the transition. In other words, I can drive them so hard that despite the fact that they want to be here thermally, if I'm driving them really hard, I can drive them only to the point where they're half and half, right? That's what thermodynamics says. I can't drive them past that, okay? But I can drive them to the point where they're half and half. Now, in this case, what if there happens to be a weak coupling between the I and the S? And I'm going to specify that the coupling happens between these 2 states. In other words, this is a 0 quantum transition where the spins mutually flip. It turns out that this is a prevalent transition a lot because of the hyperfine interaction, right? Because a lot of times an electron will overlap a nucleus and you'll get this kind of interaction, okay? And the thing about it is nature doesn't care how it gets there. It just wants to get there. And so it sees this connection and says, hey, I found a way that I can return this sample back to thermal equilibrium, even though this idiot insists on driving it to the point where the population is equilibrated, or is half and half to each. And so it says, okay, I'm going to get to work. I'm going to put some atoms down here. Now, over here, you're still driving this transition hard, and so everybody gets equalized again. And repeat, and equalize. And now nature's happy, okay? Nature's happy because of this, the place that there is a connection and no RF driving field, a double or this 0 quantum connection, there's more of these atoms in the lower energy state. But now what you notice has happened is the same ratio of populations that we had for the electron states is now with the nuclear states. There's twice as many in the up nuclear state as in the down nuclear state. This is the first form of what's now called dynamic nuclear polarization. If you go to NMR conferences, there's whole days of this. Okay? But it started here in the 1950s with this guy, and this is a theoretical prediction from Overhauser. And what you see is that you get an electron-like polarization in the nuclear spin sample, an enhancement of like a factor of 1,000. Really cool. Okay? So Overhauser proposes this theoretically, and there's a great story from Charlie Slichter about him having to get up and give a talk. Overhauser went out of town or something. And what I will say, I'll go back to this, what I will say is I love this precisely because it's one of these things you see in physics every once in a while where there were a lot of people, a lot of very well-respected people who said it couldn't be true. And what's more, they said it violates the second law of thermodynamics. And what I like about it is that it works precisely because of the second law of thermodynamics. And so, when you look at it carefully, and I'm not saying that, I would have seen it right away, certainly not. But upon a careful look, what you see is that people were saying, well, come on, it violates the second law of thermodynamics. Well, it precisely follows it, and that's why it works. So here's the experimental demonstration, the first experimental demonstration of this. done in Charlie Slichter's lab at Illinois. And I like to show this because this guy, Tom Carver, is kind of an intellectual godfather. He was a graduate student of Slichter's at the time. He was the first one to see this, the Overhauser enhanced signal as predicted. This is in lithium-7. Now, it's in lithium metal. It's not an atomic lithium. And so the connection, the I dot S, is with the conduction electrons. And it's weak enough, even in the a rather small magnetic field that was used here, so that you can write things with the hierarchy that I showed. And here you see no saturation of the conduction electrons. And here you see the lithium-7 resonance with saturation, the strong RF saturation. And this is a proton resonance just for comparison. As you can see, even in the relatively low moment lithium-7, you're already getting signals, relatively speaking, that are just blowing away signals that sort of the conventional canonical signals that you get from protons. So anyway, what I was going to say about Carver is that, well, I'll say more about him in a minute because he had a lot to do with spin exchange, but he was also, he eventually ended up at Princeton University as a professor and unfortunately died suddenly of a heart attack about 1979 or 80. And the person who took his place at Princeton was Will Happer. And Will Happer was my PhD advisor, and so I used to go around the lab and see things that had Carver's name on them, like regulators and boxes of things, and so that's kind of my connection. In any case, you should know that we have other fairly famous students of Charlie Slichter floating around the room, Dave Alien, for instance, and let's see, there was one other connection I had to Charlie that I thought of the other day that I can't remember now, but anyway, I might think of it. So anyway. What's that?
Well, I mean, Garrett is
yeah, it was. Anyway, the reason I'm bringing all this up is that these pioneers, these optical pumping pioneers, one of them, who I'm circled here, this is Marie-Anne Bouchiat. She actually traveled to Princeton in 1958, and we're pretty sure she was the first female scientist ever to work at Princeton. And she worked for Carver. And Carver was fresh off his stint with Slichter, thinking a lot about the Overhauser effect. And these are the first guys that produced something called hyperpolarized noble gas. So I'll tell you that what we're going to do is we're going to take all those polarized electrons and we're going to pump that angular momentum into the nuclei of noble gases. And so we call them hyperpolarized because they're way beyond thermal. Thermal is, a part in a billion or something, and this is like 30% or 50% polarized. And so this is the first paper. It's from 1960. And you can see right away that it was connected to the Overhauser effect because the statement in the first paragraph is that the Overhauser effect should work not by the dipole-coupled relaxation of saturated paramagnetic impurity toward a polarized equilibrium. In other words, the nuclei got polarized because despite the fact that you're saturating the electrons, there's a drive for them toward the thermal equilibrium population. And that drive is being picked up by the nuclei, and that's where you get the polarization. So you can do the same thing if you drive the system not to saturation, but drive it to 100%. And that's what we do with optical pumping, is we drive that system to 100% polarization. And now we bring it into contact with a similar contact interaction, Fermi contact interaction with our nuclei. And the fact that the rubidium, highly polarized, want to move now toward a depolarized equilibrium, they're giving up their spin. Well, who are they giving up to? They're giving it up to the nuclei, at least in part. And that's what's allowing us to produce these so-called hyperpolarized gases. So this is kind of my little picture of it. There's an interatomic Fermi contact interaction. Now, the big difference is, and this is the difference that you'll see with times, the big difference is that it only happens during the collision. So the rates are going to be a lot slower. But basically, this is what happens. Okay? They collide. There's a contact interaction during the collision. This happens. And now if I take this rubidium atom, the laser's still on. And so he'll flip back up, and he'll do the same thing with another xenon atom, and so on and so forth. And now that angular momentum that started in the light, after all, right? That's where it started. It used the electrons in the rubidium as a kind of a pathway, and then ends up stored in the nucleus of these noble gases. And it turns out that, well, it's a process that is very similar. I showed you this business of the inner core electrons. The same thing happens during the collision, except now that rubidium is encountering a spherically symmetric core of electrons around a noble gas. And it gets sucked in. It gets sucked in because if it gets a little way in, then suddenly the electron shell or the electron density around outside of its radius doesn't contribute anymore to the electric field. And so it goes in a little further, and it goes in a little further. And so you end up in a situation with like xenon, where you've got a ton of electrons, 54 of them, that here for an interatomic distance of 4 angstroms, the density at the nucleus of the rubidium atom itself, its own hyperfine coupling, is just as big as at the nucleus of the xenon atom that it's colliding with. And so these lead to transfer rates on the order of half minute, minutes. Helium, not so much. Not so many electrons. Not so much sucking. Okay? So a lot slower. The time constants here for transfer of the angular momentum are more like hours. Okay? Right. It works. And I'm just showing you some basic equipment in the laboratory. You've seen or being passed around as a sealed cell. We can make cells that have valves, so we can put the gas in, pump it up, let it go for whatever purpose you want. It turns out that with xenon 129, it's strategically useful to polarize it on the fly to take advantage of the fast spin exchange rates, and so we flow it through long tubes. There's no scale here, I apologize. This is about 6 feet or so. So big hoops, and we flow the gas upward this way, and we put laser light down through the long tube this way. This is a laser up here, and then it flows out, and we can actually freeze it, and the polarization survives the phase transition, and then we can do condensed matter physics with it, or we can thaw it, and we can image lungs, and we can do all kinds of stuff. Here is this is a typical free induction decay at 30 Gauss of say, a 5-atmosphere helium-3 sample, and there's no noise. The signal's enormous, and it just represents the fact that the enhancement of the polarization over thermal equilibrium is some 4 or 5 orders of magnitude. So we always say you can hear the spins because we can do NMR at audio frequencies, right? It's not usual that you do that. Not usual. Okay. And here you can see how benevolent I am as a boss in lab. This is a 60-hour measured T1, and clearly I've allowed the graduate student to go home and go to sleep between, right? Okay, so it takes a while to measure a 60-hour T1. That's just short of 3 days. So you have to measure for several times that. And okay, this one is room temperature. Yes, this is room temperature. Anyway, because they're alkali metals and because we care a lot about things like wall relaxation, which is a whole separate talk that I won't get into today, we do have a vacuum and gas handling system for filling these cells that we treat with some care. We care about the purities. We care about what's getting on the walls, what's getting in the system, what kind of contaminants there are. So it's a reasonably high vacuum system. And here you see various bottles of xenon, some enriched in isotopes and helium-3 and so on that we use to fill cells. We'll stick a glass manifold on the end of this and fill the cells that way. So some applications of spin exchange optically pumped noble gases. So they're noble, they're inert, and they're highly polarized. So protons are dense. That's why you can see them conventionally with NMR. Gases, especially if you want to breathe them, aren't as dense. And so you make up for it with this enhancement of the magnetization. It allows you to do things like, hey, breathe this gas and I'll take a picture, a magnetic resonance image of your lungs. And that's what's going on here. This is courtesy of my colleague Bas Driehaus at Duke University. And they do ventilation images. But interestingly enough, xenon has what's called a chemical shift. It means that its NMR frequency is very sensitive to the environment that it's in. So they're actually now sensitive enough that they can take images of the part of the xenon that's dissolved in lung tissue. It gives you different information. You compare the two, it gives you different information still. So this would not be possible. It simply would not be possible without the optically polarized, hyperpolarized gas. NMR Gyro. So this is an interesting one. This is my colleague Thad Walker at Wisconsin. And these fly in all sorts of defense satellites. And they are the way the satellites stay oriented in space. And it's an optically pumped and polarized pair of xenon isotopes. So there's a little laser in there. Actually, they're just going to lasers now. They actually have a little resonance lamp in there. It doesn't even emit coherent light that optically pumps rubidium, polarizes both xenon 129 and xenon 131. So I didn't talk about the 131. It's quadrupole, so it relaxes faster. But if you're pumping continuously, it doesn't matter as much. Now you've got two nuclear isotopes that have oppositely directed magnetic moments relative to their spin. It gives you a lot of cancellation. The whole thing here, of course, is that you have one to sense and you have one that records the rotation of the object. And so you're looking at a phase difference in the spin. So you need very long coherence times. And it's pretty cool. These things are flying in satellites made by Northrop Grumman. And it's all rubidium optical pumping and spin exchange. Spin exchange, I would be remiss if I didn't give a shout out to my former advisor, Will Happer, who, when he's not antagonizing people about climate change over the last 20 or 30 years, has done a remarkable amount of work. This is a 70-page review paper on optical pumping written in 1972, which is, somebody asked me, is there a textbook? I say, that's it. It's open on my desk at all times. Polarization of noble gas atoms by spin exchange. This is one of the first. We just call it the 84 paper. It's one of the first early theory papers describing the whole theory of spin exchange. Here's one where he noted the very important contribution of rubidium xenon van der Waals molecules to spin exchange. So the spin exchange rates are fast in large measure because of these molecules. Why? It's very simple. Binary collisions last a picosecond. These molecules last for a nanosecond. That's 3 orders of magnitude. In perturbation theory, that's 6 orders of magnitude in terms of the probability for a spin flip given the time of interaction. And so the molecules there are not very many of them, but they're really important. Okay, and they make the spin exchange process go quickly. Another theory paper in 1998, which got into even more in-depth, and there were other things that were figured out at that time. And I put this one up just because if anybody's interested in learning more, this is the paper to read. I love this paper. It's Thad Walker and Will Happer in Reviews of Modern Physics. It's rather old now, but what I like about the paper is it's a classic, great review in that it starts out really simple, and I'm pretty sure there's stuff on the last page that I have no idea what's going on. It really progresses nicely, so you can go as far as you'd like to go learning about this into complexity and depth. And it's a really nice introduction. So I haven't talked at all about nuclear spin. And in fact, I told you to ignore it. And now we got to stop ignoring it. So all stable alkali metal atoms have non-zero nuclear spin. So I showed you this picture before, and it ain't right. Because these levels, particularly the ground state level, is not a single level. It's split by the spin of the nucleus. In rubidium, it depends on the isotope, but in our favorite isotope, rubidium-87, it happens to be spin 3/2. And so if it's spin 3/2, recall that when we add angular momentum in atoms, J is the total and it's L plus S. Now I'm telling you L is 0. I'm dealing strictly with the ground state. Okay? L is 0, so now if I define F as the total, where F is J plus I is the spin angular momentum of the nucleus, then I'm left with S plus I for L equals 0. And this is showing you the Zeeman splitting versus magnetic field for rubidium-87. There's 2 manifolds, F equals 2, 3/2 plus 1/2, and F equals 1, 3/2 minus 1/2. And you can see the whole thing here. This is nice. This is a Breit-Rabi diagram. It turns out that the energy levels, when you're talking about the Zeeman splitting versus the Hyperfine splitting, which is shown here for zero field, it's a completely analytically solvable problem as long as one of the spins is 1/2. Nice. Now well, I derived it once. It was 25 pages. I always say it's good for the soul. I plan never to do it again. And it's a sea of Clebsch-Gordon coefficients and just craziness that you have to work through. But you can see that it predicts the energy levels for all the magnetic sublevels completely as a function of field. At low fields, the hyperfine interaction is big compared to the Zeeman interaction, and the manifolds split according to their F number, just like they should. So the low field quantum numbers are F and M sub F, is what that really should say. But look what happens as you go out to high field. You got the high field, and the Zeeman interaction with the electron in particular starts to be dominant. And now it looks just more like an electron simply split into two levels in a magnetic field. Here's the high one and here's the low one. And this splitting out here is on the order of the Bohr magneton times the magnetic field. So this is one of these examples where you have a really nice, clean example of, all of this, of course, is in the Coulomb potential. The Coulomb potential doesn't care about F or S or S and I. So you're left with two other interactions, the Hyperfine interaction, the I dot S, and the separate Zeeman interactions. And usually we ignore the nuclear moment because it's so much smaller than the electron moment. And so this is an example where you go from good quantum numbers that are combined to good quantum numbers that are the product states. In other words, here's the big splitting due to the electron, and here is, just as expected, the four states for the spin 3/2 nucleus. Okay? So we have to reckon with this. Now, in optical pumping, the reason I didn't bring any of this up is that my light covers all of these transitions. In other words, I don't really worry. Again, I'm only using that P state as a parking place. And so as long as I can consistently pump out of all these guys, the physics that I showed you without the nuclear spin, it says it all. Okay? And so optical pumping works just fine under most circumstances, despite the fact that there's this complicated structure. And it's mostly, of course, in the ground state. The hyperfine splitting in the excited states is much weaker because the electron doesn't spend as much time near the nucleus in p states and higher states. Okay? Okay, so that's that. And oh yeah, I just told you about, here's the Breit-Rabi equation, and it allows you to compute this entirely, even in the intermediate range. So here, there's no good quantum numbers here, but this is the only, as long as one of the spins is 1/2, you can compute it. For hydrogen, this splitting, this I dot S splitting, is very, very well known at 1420 megahertz. That's the 21 centimeter line, okay, that you see coming from atomic hydrogen deep in the universe. Amazing thing. You see this. It's actually a transition. It's a very forbidden transition, obviously, because this is all in S state, and this is from the high energy F equals in hydrogen from F equals 1 to F equals 0. The only reason you see it is what I mentioned earlier about spin exchange, about the fact that these atoms can collide, and when they collide, their F states mix. And when their F states mix, it means you've got some probability to be back up in the F equals 1 manifold, and in the infinite universe where everything is, utterly tenuous and there's no collisions to bother you, every once in a great while, these things radiate from F equals 1 to F equals 0. Okay? Interestingly, for rubidium and for the heavy alkali metals, the hyperfine splitting is even larger. And it tells you something about that sucking effect. All right? Despite the fact that you have this shielded nucleus and the valence electron is very far away from the nucleus, it gets sucked in. And it gets sucked in, and the Liz spends a lot of its time on the nucleus, and so you get a fairly, even larger than in hydrogen, you get large hyperfine splittings in these alkali metals. I'll just mention here very quickly, this is just sort of a prototype cesium atomic clock, and it makes use of both regimes here, interestingly enough. So what it's got is it's got two Stern-Gerlach apparatus and a Ramsey cavity in the middle. So you separate this is a cesium hyperfine transition. It happens to be a transition that goes up between the two F manifolds. But the point is that you separate them with a very high field and a high gradient. So you separate them, you make sure that you've got one electron state or the other. And then you come into this region of very low field, and you can manipulate them with 9 megahertz or 9 gigahertz microwaves very easily. And then you go back to the high field to select them, and it goes back. And what you find here is that because you've mixed these, you've now mixed these, and there's a certain frequency at which that works. You lock to it. That's your clock. Okay? So with a little bit of time that I have left, I thought I'd actually talk about something that we've done in lab. I mean, I know people usually, I'm not applying for a job, so I figured I could spend most of the time just talking about whatever I wanted. So we work on the physics of spin exchange and the physics of optical pumping. And there's some neat things that go on. So I'll just remind you, way back when I told you about the Zeeman Hamiltonian. everything that we do that involves looking, we love to look at frequency shifts because it involves counting, and physicists love to count. And if you look at that Zeeman interaction, it's a moment in a field. So whenever I show you a shift that I'm measuring some spectral line, like a hyperfine line that's shifting. There's a moment and there's a field, all right? And the field's coming from somewhere. So in this case, what we have is whenever we deal with polarized xenon and polarized rubidium, so we've got these two polarized species, and they're sitting on top of each other a lot of the time. And that means that although I can define some sort of Larmor frequency for each one, okay, the rubidium atoms and the xenon or the helium, in the presence of the other, that Larmor frequency will be shifted, because if there's polarization involved, in other words, if all the spins are pointed one way, then every time they collide, there's a phase shift, and they add up, because the spins are all pointed the same way. And that phase shift that frequency shift should be proportional to whatever magnetization you have. We use it as a way of doing polarimetry on these samples, precisely because you don't have some kind of thermal thing, a thermal equation or equation in thermal equilibrium that you can calculate from first principles what the polarization should be. Basically, it depends on competitions between pumping rates and relaxation rates. So this is what NMR people may recognize as a night shift, okay? And where's the moment and where's the field? Well, here's the moment. This is a shift of the xenon NMR frequency. So you're a xenon atom, and you're amidst all these polarized rubidium atoms, and they're shifting your Larmor frequency because they're adding field. And so here's the moment, the xenon moment, and then there's some constants, and this is the field. And the field goes like the rubidium density. The more spins you got, the more collisions you got, the more magnetization you have. And it goes like the polarization, zero polarization, no shift. And it goes like the electron moment, which has something to do with the G factor and the Bohr magneton. And then it goes like this magical thing called kappa naught. We spent a lot of time searching and measuring and dealing with kappa naught because this thing has all the information in it about how the electron overlaps the nucleus during the collision. And remarkably, in the case of xenon, this enhancement over what you would assume, if you took all of the rubidium and you smeared it out over a sphere, and you said, and you gave it the magnetization that it has when we polarize it, then kappa naught would be 1. The enhancement would be 1. We measured the kappa naught enhancement for xenon at almost 500. And it only happens during collisions, which is, maybe 1/1000th of the time. So it's telling you just how amazingly strong this overlap is, okay? That during these infrequent collisions, there's enough overlap that it generates a huge enhancement in the magnetic field, okay? So here, K is the nuclear spin, I equals 5/2 is the rubidium 85 nuclear spin. I don't know why it's that specific. We usually do 87. It doesn't matter. The point is we have to measure this. If we can measure it, then we can turn around and use it as a calibration to do polarimetry on these samples. And so here's the night shift I just talked about. There's a complementary shift of the EPR line of the alkali-metal due to the polarized xenon, and it has the exact same kappa naught because it's the same overlap. And so what we did in one of our experiments is we measured this guy by looking at the shift of the NMR frequency in the presence of rubidium that's polarized one way, and then if you turn a quarter wave plate, you can get to polarize the other way real fast, okay? Because that change is a lot faster than the change of the nuclear magnetization. And when we did this, so this is what we expected to see, and this is just showing the directions of the magnetic moments. This is done in a cell, just like the one I'm passing around with a laser, okay? And we have xenon and helium-3 in the cell, and the reason helium-3 is there is that the kappa naught is known for helium-3, so we're going to measure both and take a ratio, okay, to be able to extract the number for xenon. And so this is what we expect to see. We expect that if we have the rubidium moment pointed one way, we'll get a shift in one direction. This is the xenon line. And then if we flip it around, we should see a shift on the other side. Okay, so here's the rubidium in green one way, and then we flip it around, and we should get a shift the other side. Same with helium, except a lot smaller, for reasons that I told you. It doesn't have as big a contact interaction, okay? But we can measure it. There's a few hertz. We're doing this at a tens of megahertz kind of magnet field. So here's the core wave plate reversal. This is what I expect to see, and I see a mess. Holy cow! So the helium looks great. So here's, you see, where we reverse the core to wave plate with the helium, and we get this nice little shift, small but measurable, and it gets bigger as you go up in temperature. Why? Because the rubidium number density is getting bigger. Okay, so there's more magnetization, so there's a bigger shift. You can't go infinitely high because eventually you run out of light to be able to pump the rubidium, and then that equation goes to 0 because p rubidium, the polarization of the rubidium, goes to 0. So that was easy enough, but then this xenon was just crazy. And this we had fun with because we had to figure out what these multiple peak things mean. You can see there's some shifting going on to either side of equilibrium, but there's double peaks, and they're really fat. And it turns out that this is nothing more than dispersion of that night shift. In other words, if we block the laser so the rubidium is completely unpolarized, that NMR line is right here in this very narrow gray. It's only when we unblock the laser, and it turns out, of course, that when we pump these cells, the rubidium polarization is a function of position in the cell. It's often much more polarized in the front than in the back. It drops off exponentially, so actually it really drops off almost like a sharp cutoff, and that explains the two peaks. One is really zero polarization rubidium, and the other one is polarized rubidium, so it's almost like the cell was half and half as opposed to a gradual fall off. And you can ask me, well, why is the zero peak shifted away from the middle? And that's because of diffusion. And there's a whole theory you can work out, and we did, that talks about how it's almost like chemical exchange, if you're familiar with that from NMR, is that these two peaks actually start to merge under conditions where the helium or xenon can move around significantly on the time scales of the spin exchange time constant.
Is that like motional narrowing?
It is like motional narrowing. And in fact, if we go take this to an extreme, it would then narrow to a single narrow peak. That's right. That's right. So we had fun with this. We figured it out. Here's the other example. This is why I get ahead of myself. This is why you have the two peaks. So basically, the light just stops polarizing suddenly, and you get 0. And okay. And that's the line with the laser blocked. It shows you that it really is the night shift dispersion. Here's the data where I said we measured this enhancement factor, and it's about 500. So this is a lot of data. It was published in PhysRev Letters a few years ago. We beat the best result. There's actually, this paper hasn't been cited that many times, but it's been cited by some pretty crucial experiments that are using magnetometers to search for things like T violation and CP violation. So they use helium and xenon co-magnetometers, both optically pumped. And the xenon is supposed to be much more sensitive to new physics. I'm not sure why, but it is. So the helium is the one that's the standard, and the xenon is the one that's looking for, take your pick, anyons, skyrmions, dipole moment, permanent dipole moment of the atom, whatever it is. Okay. So this is cool, and this is going to allow us now to turn it around and use electron paramagnetic resonance to do polarimetry in our xenon setup. And I realize it's late, so I'm just going to say real quick that the next thing that we're doing is we're actually doing optically generated EPR, optically detected EPR of this rubidium in the regime, this regime, very, very low field regime, where everything is almost linear, not quite linear. These split apart because there's just a little bit of an effect of these lines starting to split apart. And what we do with it is now we can do optically detected NMR at 30 Gauss. So what you're seeing is a locked oscillator. It's a voltage-controlled oscillator that's locked on, just like an atomic clock, that's locked on to a specific hyperfine transition rubidium. And what I do, and it's got polarized xenon in there. And it's being polarized because there's polarized rubidium that's generating the EPR in the first place. And I can NMR destroy the xenon. That's what happens here. Vroom. And it's a locked oscillator, but it can follow. It's good enough that it can follow. So it follows. You follow here, 8 kilohertz shift. And now I'm watching the xenon polarize again from that polarized rubidium back to its saturated kind of equilibrium, polarized, and then I'll destroy it again. Boom, and here it is. So I'm doing NMR, and I'm measuring these time constant transients using one of Christoph's favorite tools, optically detected EPR. And I think I'll be done at this point and say that there's a couple pictures of my group, one a little bit older, one relatively newer. These are some of the students and undergraduates. I'm very grateful to the Access Program and to Europe for bringing all these really good students through my lab. And I've droned on a long time. I really thank you for your attention. Thanks.
Okay, I think Ben has to take off.